Okay, so there's a lot we need to cover this week, and we're going to start with the chain rule. So I want to explain the chain rule in a number of different ways, and the first way I want to explain it is just a little word problem. Okay, let's say I want to go into business selling t-shirts, and this is just like a supply chain discussion. So let's say I'm buying my t-shirts from a friend in France who gets them from a friend in India. And the friend in France buys them for, I didn't say what. Oh yeah, for 1,000 rupees. So like each t-shirt is 1,000 rupees. And let's say there's 88 rupees for €1, and you get, I got this hold on, I got the rate backwards on the other one. Okay, so you get 85 euro cents for a US dollar. Okay, so we want to know how much the t-shirt actually costs in US dollars. Okay, so this is exactly what the chain rule does. It's just comparing rates of things. So let's say we want to know that. So we would just do a little dimensional analysis. You put a whole bunch of fractions side by side and put some units in there. So 1,000 rupees, the first one is just over 1, okay? And then the next one you want to put rupees on the bottom. And you're converting between rupees and euros. And the next time you're converting between euros and US dollars. So you know that you want the rupees to cancel out and you want the euros to cancel out so that you get the price in your US dollars, right? So how many euros per rupee or rupees per euro, it doesn't really matter which one you put in as long as it's consistent. 88 rupees for €1. And then you get 0.85 euros for a US dollar. And so then we can just calculate this. Okay, so what do we get? We get 13.36. So it's about $13.37. So you're $13.37. I hope it's a really nice t-shirt. Okay, so that's how you would do that. But the point is you're looking at different rates relative to each other, and whether the rates are changing or not, it doesn't matter because you're kind of just like looking at a snapshot in time. But you got to get all those units to work out. You got to get rupees to cancel out, you got to get euros to cancel out, and then the units you're left with is dollars. And that's the same exact thing. I want you to think about this when you're doing these problems. I want you to think about how you're going to get this to work, and it's going to have that same feel to it. Okay, so for example, let's do something algebraic. What if f is x squared and g is e to the x, and I want f of g of x, and then I want to take its derivative? Well, we could just put all this stuff together, and in this one case we end up with something that simplifies down nicely, but let's pretend we didn't know, okay? So in this case we could use this trick. Since e to the x is squared, we can turn this into a product rule, and we get first times the derivative of the second plus the second times the derivative of the first. And that means we get 2 e to the 2x. Okay, and this was e to the x squared. Well, you might be noticing that well, maybe you don't notice that yet. Maybe you don't notice that you're treating this guy as though it's its own variable, and you're seeing this guy being treated like x squared, then times the derivative of the stuff inside. But that's going to become more apparent. Rather than using Newton's notation, let's use Leibniz notation. Leibniz. I like Leibniz notation, and I like Leibniz cookies too. And when I teach this class in real life, I bring cookies to class. But I don't think we're going to be doing that for a long time. So you can think of it this way. F is t squared, and t is e to the x. Then this is going to start looking like our t-shirt example. df dt, that's Leibniz notation, is 2t. And then what we're going to do is we're going to come over here and say, well, dt dx is equal to e to the x. Then, if we bring these guys together, df dt times dt dx, Leibniz says you can cancel these guys and find df dx is equal to 2t times e to the x. Now that's just inconvenient because t is stuck in there, but that's okay. We know t is e to the x. So we just stick e to the x back in there, and again, this thing simplifies algebraically. It's kind of convenient that way. So if you can think this way, then this would help. Here, I'm going to do another example with that Leibniz notation to see if it can make some intuitive sense to you guys. Okay, so if we're going to just go ahead with two polynomials because they're really easy. Now you could obviously just figure out that that's really x to the 6th, so the derivative should be 6x to the 5th, but we're going to try to get that a different way. Okay, so instead of writing it this way, I'm going to actually write f as t squared and then t is x cubed so that I can see how this works. So I'm going to do f of x cubed, right? And I want that derivative. So df dt is equal to 2t, and then dt dx is 3x squared, and I put them together, so multiply them together. Df dt times dt dx, these guys cancel, and I get df dx is 2t times 3x squared, but again, we have to replace t with x cubed. So you get 2x cubed times 3x squared, which is 6x to the 5th, which is what we promised we would get in the first place if we had just composed that in the most logical way possible. Okay? So anytime you want to use Leibniz notation for chain rule, that's fine by me. I think it makes a lot more sense. But we kind of get so used to using Newton's notation for other stuff that we just go ahead and use it. Okay, I'm going to give you some more examples so that you'll recognize these kind of formats on the worksheet. So what if we have something like this? We want to find the derivative. So we take the derivative of this mess, think of that as being the t, and so that's 4t cubed, but then dt dx is going to be 9 x squared minus 7. Okay, so this part is like your t, this part is your dt dx, and this part is your df dt. Okay? Let me do another one. What about if you do something like this? Okay, so this guy can be rewritten like so, and then the derivative is going to be like that. Again, what do the pieces look like? Well, if this piece is my t, this is like t, then first I take the derivative with respect to t, then I multiply by dt dx right there. So this whole mess is dq dt. Okay? So I have a visual for this, and I hope you'll appreciate this. Whenever I do the chain rule, I think about frog dissection. Okay, so humor me a bit. When I was in high school, I did a lot of dissections, like I dissected a worm, I dissected a frog, a pig, all sorts of stuff, right? I think I did like some kind of shark. It was a lot of fun. But one time, I think it was the frog we were dissecting, and there was a fly inside the stomach of the frog. So I thought, this is great. I get to dissect the frog, and then I get to dissect the fly that was inside the frog. And so when I'm thinking about calculus, and I'm thinking about this, I think, okay, if I have my little frog, there's my frog, and inside the frog, there's a fly, and maybe I got really lucky. Maybe I'm dissecting a snake that just ate some kind of a frog that had a fly inside. If you want to dissect all this stuff, you have to first dissect the snake, put the snake parts here, and then you have to dissect the thing that was inside, which was the frog, so the frog parts go here. And then the thing inside that is the fly, so you'd stick the fly parts over here. And so in math, you're just going to multiply all those guys together to get the overall derivative. So you just keep multiplying. It doesn't matter how deeply it's nested. You just keep multiplying by the thing inside, and the derivative of the thing inside, and the derivative of the thing inside, and the derivative of the thing inside, and you just multiply all that mess together, and then you've dissected the whole thing. Okay, concavity. I want to make sure I tell you about concavity. So concavity has this relationship to the derivative. So let's go back to this thing first. If you have a max or a min in your function, then the derivative has to be 0 there. But the implication doesn't go the other way, so what we do is we still take the derivative, set it equal to 0, and look for potential max and mins. We have exactly the same relationship with points of inflection. If you have a point of inflection in your function, the second derivative has to be 0. Yeah. So, and again, it doesn't go the other way. But it usually does. I mean, for these exercises, it usually works. But you got to check, because you can have something like, x to the 6th that looks kind of like this. It has a whole stack of zeros at the origin, but it doesn't mean it's a point of inflection. It's actually a min. So just because you have a 0 there, a 0 in your derivative or second derivative doesn't guarantee whether it's a max, min, or point of inflection. It just means it's in your pool of things to investigate. And then you have to kind of work out the details along the way. Okay, so when you're looking to find the concavities, so like when your function is going up, we say it's increasing, and when it's going down, we say it's decreasing. And we have an analogous situation for points of inflection. They split the curve into pieces that are concave down, so they spill water. I think we talked about this. Or concave up, they catch water. We've done this before visually, but now because we have this derivative rule, we can use that to help us investigate something. So for example, in the worksheet, you're asked to figure out where the concavity changes. You should use a combination of several tools. If it's a complicated function, you might want to sketch it on Wolfram Alpha, but that's not going to tell you exactly where the concavity changes, but that's going to give you a general idea of what the function looks like, so that you can do this thing theoretically and then get a gut reaction out of your plot and say, oh, okay, that looks like it's in about the right place. So you should work this from both ends. You should get plots on Wolfram Alpha so you can get a picture in your mind of what you're trying to do. But then you should just really work out all the calculus to make sure everything connects up the way it should. Okay? So that's specifically I'll just tell you which function I'm talking about. E to the minus x squared is the one I'm talking about. And it looks like this, more or less. But you play with that and figure out where the concavity changes. Okay. So the next thing I want to talk about is these graphs that are piecewise linear. So let me try to draw one. Okay, hopefully this function won't be too bad. Okay, so I'm going to try to come up with an example for you. If I want to find the derivative of f of g of x at x equals, let me try 1. Here's the process. And you're going to have to do this over and over again on this and several other worksheets. First of all, you need to find out what g of 1 is. You're also going to need to know what g prime of 1 is, but you're also going to need to know f prime at g of 1. So as g of 1 happens to be 1, but I'm going to change the color to red so that you know this is the one down here. The output one is the one. Okay? G prime of 1 happens to be 1, and f prime of 1 is negative 1/2. But I wanted that to be black. Blah. Sorry. Okay, so what I want to do is I want to multiply the two derivatives together to give me negative 1/2. Okay, so part of the problem is we think of this as f of t or x, and we use the same variable for the other plot. But when you're feeding one of these into the other, it kind of makes more sense to think of this. Like g is a function of x, think of it this way, and then f is a function of g. So don't put an x over here. We put an x there to mean that it's just some kind of variable. But I want you to imagine that one of your plots is f of g and the other one is g of x. Okay? And that will just help clarify that in your mind. And of course, then we switch the position, because like later then we'll say, what about g of f of x? So then they switch roles. But in this particular configuration, this is what we're after. Okay, so let's go ahead and do another one and see if this makes sense. And try another one. I'm going to set it up. Now you may end up, if you end up with asking, for example, the derivative at 2, you're going to get a mess. So that would be a does not exist situation, because the function is continuous, but the derivative doesn't exist there. Okay, so we want to try something like x equals 3 and push our luck. Hopefully we don't run into one of those corner cases. All right, so you think about this, pause, and then come back and see if you agree with me. Okay, let me try that. So g of 3 is what? G of 3 is actually 0, and we already killed this problem because f at 0 has a derivative that does not exist. So we can stop that problem. That's a does not exist situation. Okay, let's try another problem now. Okay, let's try x equals negative 1. So you try that and come back. Okay, g of negative 1 happens to be negative 1. Okay, so again, we're going to make this thing red so we can be clear which negative 1 is going down here. So we also need g prime at negative 1. G prime at negative 1 is 1. F prime at negative 1 is negative 1. So we should multiply these two derivatives together and get negative 1. Let's do one more. Let's try one second. Okay, I'm going to try x is equal to 1/2 and see if that does anything useful. G of 1/2 is 1/2. Well, 1/2. F prime at that value is negative 1/2. G prime at this same, my computer is not cooperating with me today. G prime at 1/2, and that's that same 1/2. G prime at 1/2 is 1. So I'm going to multiply these two derivatives together to get negative 1/2. Okay? So hopefully that'll get you through the homework exercises, or rather the worksheet exercises. And I think you might have some web work questions like that too. So one thing I kind of wanted you to think about is, let's say I have a function f, and right now this is going to be 10, but I'm gonna squish this thing. I'm going to speed up this function. I'm going to paste a copy of it, but I'm going to squish it, so it's actually going to be f of a half. And I want it to be, yeah, that's about right. It's roughly, it's good enough. Okay, so this guy is f of x, and this guy over here is going to be f of 2x. I want you to think of this coefficient here, this multiplier, as being the speed at which I'm running my function relative to the original function I took it from. So for example, if this is 10 over here, this guy is only going to be 5 over here. So for example, if we know what the derivative is over here, let's say the derivative is 2, then the derivative over here must be 4. All right, so you have to not only dereference where that came from on the original function and say, well, that was a derivative of 2 over there, but now we have to take into consideration this speed factor, which speeds everything up by a factor of 2. So you have to have both of those derivatives. Like the derivative of this whole thing has to be multiplied by the derivative that you found over there. So maybe this visual will help you understand why we keep multiplying derivatives together. Just sort of get this picture in your head, and maybe that'll help things congeal. Okay, so I want to show you how to understand why the derivative of natural log is 1 over x. It's fine for you to just know it, but I would really like you to understand it. And to do that, you have to start by understanding the derivative of e to the x being e to the x. So this is 1, and a natural log has this mirror image look. So this is natural log of x, and this is e to the x. And so for any, move that a bit, for any point that you have in natural log of x, you have an analogous point in e to the x. And because of this, is this sort of mirror imageness, whatever the slope is in one place, it's the reciprocal of the slope in the other place. So if the slope here is 1, this slope here is still 1. But if this slope is 2, then this slope would be a half. So it's a reciprocal because it's in a mirror image relationship through the y equals x line. Okay? So if we have a point here, let's say we have x comma e to the x, and we're going to label the point here. And here I'm going to label this y comma natural log of y. And the reason I'm using both x and y is that I can put them into this relationship. So this e to the x is equal to y, and x equals natural log of y. So x equals natural log of y, and y equals e to the x. And that way, I really only have two values floating around, but I'm writing them two different ways. Okay? Now, I happen to know that the derivative over here is just, so the slope of the tangent line is e to the x. Well, what is e to the x? It's y. So that means the slope over here, this slope, has to be the reciprocal. So this slope is 1 over e to the x, or 1 over y. But that is the function. You know, we had function of y is natural log of y, so f prime is 1 over y. But you say, we're not using y's, we prefer to use t's or x's, and that's fine. Okay, so y equals t, I don't care. Change all those y's to t's, and you got yourself a deal. Okay, so the derivative of natural log of x is 1 over x. The derivative of natural log of t is 1 over t. All right, so this whole exposition is there to help you understand one of the questions on the worksheet, and I'll leave it to you to figure out which one it is, But I'm going to give you one more clue about that. And that's this deal that if you have some function, and some function, let's say of x, dy dx equals blah, 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 blah. Okay? You can simply take the reciprocal, I'm going to say this is q. Then it's true that dx dy equals 1 over q. This is a special buy one get one free on derivatives, but only for the first derivative. So you can't do this with the second derivative. There's no trick that you can do like the derivative of this thing and get the second derivative of the reciprocal or something crazy like that. There's a very special thing going on because when you're taking just the first derivative, there's this symmetry between dy dx, and then literally if you take the reciprocal, you get dx dy. Again, just a deal that works only in the first derivative. It's pretty cool, and it's a trick that often allows you to cut steps in problems. Okay, and I'm pretty sure that's all you need to get through worksheet 15, and I'll see you in class. Take care.